In this video, I'm going to show you how to apply the central limit theorem to an example. I think you'd find it's a lot easier to follow if you're with me in the text as we go through this. So take a look at page 439. In particular, we're going to be working on problem number 22. Problem says upper leg length. The upper leg length of 20 to 29-year-old males is normally distributed with a mean length of 43.7 centimeters and a standard deviation of 4.2 centimeters. Part A is asking, what is the probability that a randomly selected 20 to 29-year-old male has an upper leg length that is less than 40 centimeters? Now, it's probably helpful to notice that in Part A, the sample size is 1. We're asking about the probability associated with one individual from the sample. So if you were to put this in probabilistic terms, we're asking what's the probability that x, which is the normal random variable associated with upper leg length, is less than 40. So this is a left-tailed problem, and we're going to use the normal CDF. The lower limit would be negative infinity, so we'll put in the calculator's proxy for that. The upper limit would be 40. The mean is 43.7, and the standard deviation is 4.2. And there's your probability. Now part B is asking something similar, but notice here that the sample size is 9. It says a random sample of 9 males who are 20 to 29 years old is obtained. What is the probability that the mean upper leg length is less than 40 centimeters? Now in this case, the central limit theorem applies. And if you look at page 438 in the text, you can see that little table right there that summarizes what the central limit theorem says. So we know that the mean of the sampling distribution is going to be mu. It's the same as the population mean, 43.7. And the standard deviation of the sampling distribution, sigma x bar, is going to be sigma divided by root n. So in other words, 4.2 divided by root n. It's also helpful to notice that in the case where n is equal to 1, 4.2 divided by root 1 is 4.2. So you could say that the central limit theorem still applies when you have a sample size of 1. But we normally don't go through that extra work in the calculation, we just calculate it directly. This is also going to be based on a normal CDF, and we'll let the calculator do the arithmetic for us inside the calculation. So again, this is a left-tailed problem, so the lower limit is also negative infinity. The upper limit is still 40, and the sample mean is still 43.7. The standard deviation is what's different. And so in this case, we can let the calculator do the calculation for us. Sigma x bar is going to be 4.2 divided by the square root of 9. Now you could have worked that out outside the calculator, but most people find it's easier to work it out on the screen like this. Just let the calculator do the arithmetic. There's your probability right there. Part C is asking, what is the probability that a random sample of 12 males who are 20 to 29 years old results in a mean upper leg length that is less than 40 centimeters? So notice the sample size is increasing, and we can simply recycle our key sequence here and go in and edit that a little bit. It looks like there's a bug in my calculator emulator software here. It's extending the radical over the parentheses, which it's not supposed to do. But anyway, let's just change that to a 12 right there, and then put another closer on that. So there's your probability right there. Now notice it's smaller, quite a bit smaller, by almost a factor of 4. Part D is asking, what effect does increasing the sample size have on the probability? Provide an explanation for this result. Well, you can see clearly that increasing the sample size decreases the probability. And again, the reason for that is because the standard deviation changes when the sample size changes. So when your sample size is 9, your standard deviation is 4.2 divided by root 9. which is 1.4. But when your sample size is 12, your standard deviation is smaller. Which means that your distribution looks different. Has a taller peak and has narrower tails, if you will. And so of course that's going to change the probability. So if you think about the formula, sigma x bar is equal to sigma divided by root n. How does that behave as n increases? Well, sigma x bar is going to get smaller, and that's why the probability changes. Finally, part E is asking, a random sample of 15 males who are 20 to 29 years old results in a mean upper leg length of 46 centimeters. Do you find this result unusual? Well, let's consider what are the chances of getting a sample of 15 males who have an upper leg length that's greater than or equal to 46 centimeters. This is also a normal CDF, and in this case it's a right-tailed problem. So our lower limit would be 46, and our upper limit would be positive infinity. The mean is still 43.7, and the standard deviation now would be sigma over root n, so 4.2 divided by root 15. Close the root, close the normal CDF, and there's the probability right there. Now, if you recall, when they ask whether something is unusual or not, or unlikely, what they're really asking is the probability associated with that event less than 0.05? And you can see that in this case it is. So we would say yes, this is unusual. And if you think about why, well, we have a population, and we're told that the mean length for the upper leg is 43.7 centimeters. So in order to get a sample of 15 individuals with the sample mean being greater than 46, greater than or equal to 46, you'd have to have quite a freak sample. You'd have to have a lot of, basically all the individuals in the sample with very long upper legs. And when you have more than one, that's very unlikely. Individuals are a lot more variable than samples, because in a sample you tend to have some with short legs, some with medium legs, some with long legs. And the larger the sample, the more true that is. So this is very unlikely. As you can see, its probability is 0.016, which is considerably less than 0.05. In the next video, we're going to show you how to apply the central limit theorem to population proportion.